The National Electrical Code, or NEC, does not specifically prohibit connecting bare and coated ground wires. It does provide general guidance on grounding and bonding. NEC Section 250.118 states grounding electrodes shall be interconnected and bonded together to form the grounding electrode system. NEC Section 250.125 permits the use of bare or insulated conductors for grounding electrode system connections. When dealing with healthcare facilities, additional requirements are present because of the critical nature of these environments. NFPA 99 Healthcare Facilities Code 2021 edition, Section 9.3.2.12 states that equipment grounding conductors shall be insulated, covered, bare, or insulated and covered. Section 9.3.2.13 states that equipment grounding conductors shall be readily identifiable as grounding conductors and shall not be used for any other purpose. Based on the NEC and NFPA 99, it is generally acceptable to connect bare and coated ground wires in a healthcare facility built around 1965. However, precautions must be considered. The coated ground wire should be clearly identified as a grounding conductor. The connection between the bare and coated wires should be made using an appropriate mechanical or electrical connection method. The connection should be inspected periodically to ensure proper continuity and integrity. It is recommended to engage the services of a qualified electrical engineer or electrician to assess the specific installation and determine the appropriate course of action. For clarity, firstly, the National Electrical Code establishes the foundation for electrical safety in buildings. Secondly, it covers various aspects of electrical installations, including grounding and bonding requirements which are there to protect people and property from electrical hazards. Thirdly, the NEC provides guidelines on how to properly ground electrical systems to minimize the risk of electric shock and fire. Grounding ensures a lower impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Fourthly, grounding electrode systems are crucial for establishing a reference point for electrical systems, and they typically involve connecting electrodes such as ground rods, metal water pipes, and building steel to form a comprehensive grounding network. Fifthly, bonding involves connecting non-current carrying metal parts of electrical equipment and systems to create an electrically conductive path. Sixthly, this path helps to equalize voltage potential and reduce the likelihood of electric shock. Seventhly, in healthcare facilities, electrical safety is of paramount importance due to the presence of sensitive medical equipment and vulnerable patients. Eighthly, NFPA 99, the Healthcare Facilities Code, provides additional requirements for electrical systems in healthcare settings to ensure a safe and reliable environment. Ninthly, NFPA 99 addresses essential electrical considerations such as isolated power systems, equipotential grounding, and minimizing leakage current to protect patients and staff. Tenthly, the code emphasizes the importance of redundant grounding and bonding to create a safe electrical environment for medical procedures and patient care. When connecting bare and coated ground wires, several factors must be considered to ensure compliance with electrical codes and standards. 1. The primary concern is to maintain the integrity of the grounding path, providing a low impedance route for fault current. 2. The connection method should be appropriate for the wire sizes and materials being joined, ensuring a reliable and durable electrical connection. 3. It is crucial to properly identify the purpose of each ground wire, distinguishing between equipment grounding conductors and grounding electrode conductors. 4. Equipment grounding conductors typically carry fault current from electrical equipment back to the source, while grounding electrode conductors connect the grounding system to the earth. 5. When connecting bare and coated ground wires, it is essential to use connectors and methods that are listed and labeled for grounding purposes. 6. These connectors are designed to provide a secure and corrosion-resistant connection, ensuring long-term reliability. 7. It is advisable to use mechanical connectors such as compression connectors or set-screw connectors, which provide a robust and reliable connection compared to relying solely on wire twisting. 8. In healthcare facilities, additional precautions may be necessary to minimize the risk of electrical interference and ensure patient safety. 9. Isolated ground receptacles and isolated power systems can help reduce electrical noise and leakage current in sensitive areas such as operating rooms and intensive care units. 10. Regular inspections and testing of grounding systems are essential to verify their effectiveness and identify any potential issues. 11. Visual inspections can help identify loose connections, corrosion, or damaged conductors, while electrical testing can measure grounding impedance and ensure compliance with code requirements. 12. Documentation of grounding system inspections and test results is crucial for maintaining a record of electrical safety measures and demonstrating compliance with regulations. Lastly, engaging a qualified electrical engineer or electrician is recommended to assess specific installation scenarios and provide guidance on appropriate grounding practices. These professionals have the knowledge and experience to ensure that electrical systems are installed and maintained in accordance with applicable codes and standards. Grounding in electrical engineering serves several critical purposes. The primary objective is to protect individuals from electric shock by providing a low-impedance path for fault currents to return to the source, thereby tripping over current protection devices such as circuit breakers or fuses. Grounding also helps to stabilize voltage levels within an electrical system, preventing voltage fluctuations that could damage equipment or pose safety hazards. Furthermore, grounding minimizes electrical noise and interference, improving the performance and reliability of sensitive electronic devices. In the context of healthcare facilities, grounding becomes even more critical due to the presence of vulnerable patients and sensitive medical equipment. These facilities typically employ stringent grounding practices to mitigate the risk of electrical hazards and ensure the safety of patients and staff. NFPA 99 outlines specific requirements for grounding electrical systems in healthcare environments, addressing considerations such as isolated power systems, equipotential grounding, and leakage current limits. Isolated power systems are designed to prevent ground faults from interrupting power to critical equipment during medical procedures. Equipotential grounding aims to minimize voltage differences between conductive surfaces in patient care areas, reducing the risk of electric shock. Leakage current limits are established to prevent excessive current from flowing through patients or staff who may come into contact with electrical equipment. The NEC provides comprehensive guidelines for grounding and bonding electrical systems, covering aspects such as grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Section 250 of the NEC is dedicated to grounding and bonding requirements, outlining the methods and materials for establishing effective grounding connections. Grounding electrode systems typically consist of interconnected electrodes such as ground rods, metal water pipes, and building steel, providing a low-impedance path to earth. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, providing a path for fault currents to return to the source. Bonding involves connecting metal parts to create an electrically conductive path, minimizing voltage differences and reducing the risk of electric shock. When connecting bare and coated ground wires, it is essential to follow industry best practices and adhere to applicable codes and standards. The connection method should be appropriate for the wire sizes and materials being joined, ensuring a reliable and durable electrical connection. Mechanical connectors such as compression connectors or set screw connectors are commonly used for grounding connections, providing a secure and corrosion-resistant joint. It is crucial to properly identify the purpose of each ground wire, distinguishing between equipment grounding conductors and grounding electrode conductors. Equipment grounding conductors carry fault current from electrical equipment back to the source, while grounding electrode conductors connect the grounding system to the earth. In healthcare facilities, additional precautions may be necessary to minimize the risk of electrical interference and ensure patient safety. Isolated ground receptacles and isolated power systems can help reduce electrical noise and leakage current in sensitive areas. Regular inspections and testing of grounding systems are essential to verify their effectiveness and identify any potential issues. Visual inspections can help identify loose connections, corrosion, or damaged conductors, while electrical testing can measure grounding impedance and ensure compliance with code requirements. Documentation of grounding system inspections and test results is crucial for maintaining a record of electrical safety measures and demonstrating compliance with regulations. The use of appropriate connectors and methods is essential when connecting bare and coated ground wires in electrical systems. These connectors ensure a secure, reliable, and corrosion-resistant connection, minimizing the risk of electrical hazards. Mechanical connectors, such as compression connectors and set screw connectors, are commonly used for grounding connections due to their durability and effectiveness. Compression connectors create a tight seal between the wires, providing a low impedance path for fault currents. Set screw connectors use screws to clamp the wires together, ensuring a secure mechanical and electrical connection. When selecting connectors, it is crucial to choose those that are listed and labeled for grounding purposes. Listed connectors have been tested and certified by a recognized testing laboratory such as Underwriters Laboratories or Canadian Standards Association to meet specific safety and performance standards. Labeled connectors indicate the intended use and limitations of the connector, providing guidance on proper installation and application. Proper installation techniques are essential for ensuring the effectiveness of grounding connections. The wires should be properly prepared by stripping the insulation and cleaning the conductors to remove any dirt or corrosion. The connector should be sized appropriately for the wire gauge and type, ensuring a secure and reliable connection. The connector should be tightened to the manufacturer's specified torque to prevent loosening or damage to the wires. Regular inspections and maintenance of grounding connections are crucial for maintaining the integrity of the electrical system. Visual inspections can help identify loose connections, corrosion, or damaged conductors. Electrical testing can measure grounding impedance and verify compliance with code requirements. Any issues identified during inspections or testing should be promptly addressed to prevent potential hazards. The NEC provides specific requirements for grounding and bonding electrical systems, including guidance on the selection and installation of connectors. Section 250.8 of the NEC addresses the requirements for making effective grounding connections, specifying the methods and materials that are permitted. Section 250.7 of the NEC provides requirements for the grounding and bonding of equipment, ensuring that all non-current carrying metal parts are properly grounded. Compliance with these requirements is essential for ensuring the safety and reliability of electrical systems. In healthcare facilities, additional requirements may apply due to the critical nature of the environment. NFPA 99 provides specific guidance on grounding and bonding electrical systems in healthcare facilities, addressing considerations such as isolated power systems, equipotential grounding, and leakage current limits. These requirements are designed to minimize the risk of electrical hazards and ensure the safety of patients and staff. The role of a qualified electrical engineer or electrician cannot be overstated when dealing with grounding and bonding issues. These professionals have the knowledge, experience, and training to ensure that electrical systems are installed and maintained in accordance with applicable codes and standards. They can assess specific installation scenarios, provide guidance on appropriate grounding practices, and perform inspections and testing to verify compliance with regulations. Engaging a qualified professional is essential for ensuring the safety and reliability of electrical systems, particularly in healthcare facilities where the stakes are high. Electrical grounding and bonding are critical aspects of electrical safety, providing a low impedance path for fault currents to return to the source and minimizing the risk of electric shock. The NEC and NFPA 99 provide comprehensive guidelines for grounding and bonding electrical systems, addressing considerations such as grounding electrode systems, equipment grounding conductors, and bonding of metal parts. The connection of bare and coated ground wires requires careful consideration to ensure compliance with codes and standards. The use of appropriate connectors and methods is essential for establishing a secure, reliable, and corrosion-resistant connection. Regular inspections and maintenance of grounding connections are crucial for maintaining the integrity of the electrical system. Engaging a qualified electrical engineer or electrician is recommended to assess specific installation scenarios and provide guidance on appropriate grounding practices. By following these guidelines, electrical systems can be designed and installed to provide a safe and reliable environment for occupants. In general scenarios, whether residential, commercial, or industrial, connecting bare and coated ground wires needs understanding electrical safety principles. First, it is important to acknowledge the role of grounding, which provides a low impedance path for fault currents. Second, it also serves to minimize the risk of electrical shock and fire hazards. Understanding NEC guidelines ensures compliance. Section 250 dictates the methods and materials for effective grounding connections. It defines how to properly bond electrical systems. This includes grounding electrode systems. These systems consist of interconnected electrodes like ground rods, metal water pipes, and building steel. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment. This provides a safe route for fault currents to return to the source. Third, knowing the wire types involved, whether bare or coated, influences the connection approach. Bare wires are typically grounding electrode conductors. They are directly connected to grounding electrodes. Coated wires are equipment grounding conductors. They run alongside circuit conductors within electrical raceways. Fourth, connecting bare and coated ground wires needs using appropriate connectors. Mechanical connectors like compression connectors or set screw connectors are preferable. They ensure a secure connection, resistant to corrosion over time. These connectors provide a solid mechanical and electrical connection. Avoid simply twisting wires together. Fifth, consider the environment. In damp or corrosive environments, use connectors rated for such conditions. These connectors are designed to resist corrosion and maintain integrity. Sixth, properly prepare the wires before making the connection. Strip the insulation on coated wires. Clean the conductors. Remove dirt or corrosion. Seventh, ensure the connectors are sized appropriately for the wire gauge. Use the correct tools to tighten the connectors. Follow the manufacturer's specifications. This avoids loose connections or damage to the wires. Eighth, inspect the connections periodically. Check for looseness, corrosion, or damage. Address any issues promptly to maintain grounding effectiveness. Ninth, in specialized settings, healthcare facilities, or industrial plants, enhanced grounding practices may be required. These facilities may use isolated ground systems. They may also have stringent equipotential bonding requirements. These measures minimize electrical noise and prevent equipment malfunction. 10th, keep detailed records of grounding system inspections, tests, and maintenance. This documentation helps demonstrate compliance with regulations. It also serves as a reference during future maintenance or upgrades. 11th, working with electrical systems can be dangerous. Always to energize circuits before making connections. If you are unsure, consult a qualified electrician or engineer. Compliance with the NEC is not just a matter of regulatory compliance. It is a commitment to safety. Properly grounded electrical systems protect people, equipment, and property from electrical hazards. Regularly review and update grounding practices to adapt to changing conditions and technology. Educate personnel on the importance of grounding. Ensure they follow established procedures. Ultimately, it involves creating a culture of safety where electrical hazards are recognized, risks are mitigated, and everyone is responsible for maintaining a safe electrical environment. Always adhere to local regulations and codes, because these are the minimum standards. In many cases, it can be appropriate to exceed minimum standards.